All right, so we continue with our differential amplifier. So let's change the ink over here. So this was our schematic for the amplifier that amplifies the difference between the two signals. We have a gain setting resistors R2 and R1. We have this resistor R3 and R4. And when we apply a voltage source to this operational amplifier, we see that the differential input resistance, RID, was the ratio of the voltage difference that we apply over here and the current that flows through this loop, okay? Because this is voltage here is V1, voltage here is V2, and due to virtual ground, this is a short circuit. So the current actually essentially flows through this loop, and we have this expression for VID over I, and that comes out to be 2 times R1, because we assume here R3 is R1 and R4 is R2. Okay, so we have this RID, which is 2 times R1, and the differential gain AID, that is set over R2 over R1. Okay, so if we want higher gain, we can reduce the value of R1, but at the same time, RID goes down with the reduction of R1. So that is the drawback of this circuit. We want high input resistance and high gain both. Ideally, this should be infinite, and this should as well be infinite. So how to circumvent or solve this problem? So we have another amplifier that we can draw here. What we do here to the differential amplifier, we draw another circuit. So let's say we have this amplifier right over here. So this is our differential amplifier. We know that. And this is how it can be configured. It has a gain A. And to the input side, we apply 2 voltage follower circuits as we've seen previously. So the input to this amplifier is VI1, okay? And what we do here, we have another circuitry. So essentially we have 3 operational amplifiers. Let's say this is A1, that's A2, and that's A3. And if we closely observe this, we see that we have this resistor. Let's draw it properly so that we don't have any problem in analyzing the circuitry. And we have this feedback to both of these. And these 2 outputs of these amplifiers, they are connected to this 3rd operational amplifier right over here. Okay. VI2. These are the, let's say, resistors R1, and the middle point, let's say it's X, and that is connected to the ground over here. All right. And here we have this R3, that's, let's say, R3, both of them R3. Here is R4, and that's also, let's say, R4. the values of these two resistors are 2. Okay. So if we see now this block right over here is our differential amplifier. Okay. And the gain of this amplifier, we know that this R3 and R4, they are the gain setting resistors. Right over here, we have, this is VID, that's the differential input voltage, the difference between V1 and V2. Okay. If we note these two blocks right over here, if we closely observe them, if we see these two blocks, they are the voltage followers. We've seen the module, we've covered the topic in another video. Followers, okay, and they are also called as, they act as an input buffer. So because we know that if without these two amplifiers, A1 and A2, the input differential resistance of this differential amplifiers is 2 times the value R3 right over here. Okay, so we have to make sure that the input signals that we apply, they are all applied to the input terminals of the op-amp. There is no drop right over here. Okay, so we want the input resistance of the amplifier to be infinite, and that's why we have made this provision. So this is the non-inverting configuration of the amplifier A1 and amplifier A2. You see that this is a non-inverting amplifier. So here's a VI2. So voltage right over here V1 is nothing but VI2. Okay, so this is VI2, that is V1. Okay, and V2 is right over here, is also VI2. And we know that due to the virtual ground concept, the same voltage appears at both of these input terminals. So we see here that, okay, so this is a negative input terminal, this is positive input terminal. Similarly, we have this, let's say, we have this output V2, and this is V1, and due to the voltage short, we say that V1 is VI1 right over here. Okay, it's a virtual short. All right, so this is the voltage that we have here. And the gains, output voltage, let's say VO1 would be simply 1 plus R2 over R1, VI1 right over here. Okay, or let's say, let me draw it properly. Okay, and VO2 right over here is nothing but 1 plus R2 over R1 VI2. Okay, so that's your output voltage. So we know that the output voltage is nothing but gain times VID, which is VID is nothing but a gain times VO2 minus VO1. Okay, because these are the two voltages that are coming right over, and they are getting applied to this input terminals of this amplifier. So what we have here is that these two buffers, they acts as a buffer between the input signals that we apply to this amplifier and the differential amplifiers. And additionally, they have the gains in the first stage right over here by the factor 1 plus R2 over R1. And therefore, the total gain of the circuit, we know that VO is nothing but VO1 plus VO2. We have the superposition theorem in the previous model, we've seen that. So this is the output due to output of this differential amplifier when only one voltage input is active, that is VO1 right over here, and VO2 is the input right over here, and output of the amplifier when only VO2 is active. Okay, so these two are the inputs right here. So final output will be gain times this differential signal. So that gain is given by R4 over R3, that is the gain of the differential amplifier, and multiplied by 1 plus R2 over R1 VID. Okay, so we can see that we can simplify this analysis. From the previous model, we can refer how this equation came over here, because we know that R4 over R3 multiplied by VID is the gain of the differential amplifier, and this additional gain 1 plus R2 over R1 comes because of this input voltage follower stages. So this whole circuit is termed as instrumentation amplifier. Okay, and the advantages of this circuit is that your gain is higher. So instead of one amplification stage, we have two amplification stages. So gain is higher, as we see here in this expression. Second, input resistance is higher. So ideally, it is infinite, and practically it is certainly greater than 2 times R3, as we've seen in the differential amplifier case, because we have the buffering, and we know that the input resistance of this at this stage, right, or we're looking at these input terminals of the operational amplifiers. No current can pass through the input terminals, right? We know that from the theory, the current is zero, that is trying to enter the input terminals of the op-amp right over here. Okay, right over here. So current is zero, so RID is infinite. Okay. So this is how the principle of instrumentation amplifier works. But what about, are there any drawbacks for this circuitry? Yes, certainly. What happens when we apply a common mode signal? For instance, let's say we have this circuitry and we have the signal that is common to both the inputs. Okay, let's say we have PCMI, that is common mode input signal. So obviously these two first stages, amplifier A1 and A2, they are going to amplify this VCMI with this factor 1 plus R2 over R1, which is same as differential, which is same as what they will do with the differential signals. After that, at the second stage, right over here, this VCMI, whatever the factor, which is 1 plus R2 over R1, this is the gain by which they will get amplified. They appear right over here, and because of the differential amplifier action, they will get cancelled out. Okay, so that has to be the case, but now the differential amplifier will have a larger common mode signals right over here, because the common mode signal is directly coming from this stage amplified way right over here. They are not getting cancelled at the first stage. So differential amplifier will have a higher common mode gain as well as a differential gain, the combined output. Okay, so we have to have this into consideration. Another situation is that there are two paths. The path number one is right over here. We see that this is one signal path that goes from input to output and this is another signal path that goes from input to output. So these two paths has to be matching. So it means the values of these resistors in each of the signal paths has to be ideally matching. Okay, any mismatch results in unwanted output signal right over here. So that is a drawback of this. How do we solve this problem? We can see that what we do here is we can repeat or we can draw the next signal. We'll see how we can solve this problem. So till now we just stop here, and we see in the next module how we can solve the problem of common mode rejection and the symmetry of these signal paths, and take the advantage of this instrumentation amplifier.